So let's say there is a satellite in orbit around the Earth. You have the Earth here, and this satellite of mass m is attracted towards the Earth by gmm over r squared. Okay, where me is the mass of the Earth and r is the distance between the Earth's center and this satellite. Okay, so now let's say this satellite has a horizontal velocity v. So we know that the this force, the gravitational force, is also the centripetal force of attraction. Okay, so now at this horizontal velocity or tangential velocity, it will complete one entire orbit, okay, in a time period of t. Okay, so t, where t is the time period or time of one orbit. So if you see the circumference of this circle, it is 2 pi r. Okay, and that would give you the tangential velocity. How much distance it covers in how much time. Okay, so I'll replace v square over here with 2 pi r over t whole square divided by r. Okay, so this will give me m times 4 pi square r over t square. Okay, so therefore I have gmem over r square equals 4 pi square r over t square. Okay, this implies t square over r cube equals gme. Okay, this m got cancelled off with the m over here. Okay, gme over 4 pi square. Now you see that this entire thing is constant. Therefore, t square is directly proportional to r cube. This is Kepler's law. Now the students should remember this derivation because it is quite often asked in the exams in a gravitational fields and forces question. So for an object in an orbit around a planet, the square of the time period of the object's orbit is proportional to the cube of its radius. Okay. Next part, 9.4.3 and 9.4.4 are deriving expressions for kinetic, potential and total energy of orbit. So we already know that for an object in an orbit or in any kind of a gravitational field, the potential energy is given by minus gmm over r square. Okay, so now we know that the force of attraction gmm over r square is equal to mv square over r, right? So I can cancel this r square term and r over here, and I can multiply both these sides with half. Okay, half mv squared is the kinetic energy of this satellite. So therefore, the kinetic energy can be given as gmm over 2r. Okay, so that's the kinetic energy. This is the potential energy. And if I add both of them up, I should get the total energy of the satellite. That will be minus gmm over 2r. Okay? So those are expressions for the total energy, kinetic energy and potential energy. On page 22 you can see a graph of how the total energy, potential energy and kinetic energy vary with the distance from the planet's surface. Okay? Now, after that is a little bit of a theory. Firstly is the concept of a geostationary orbit. For a geostationary orbit, the student should know that the satellite, the relative position of the satellite above the Earth stays constant. So which means that as the satellite moves, the the point below it on the Earth's surface stays the same, which would mean that the period of orbit would always be 24 hours, because that is how much time a point on the Earth would come back to its original place. So the period would be 24 hours for a geostationary orbit. 9.4.5 is discussing the concept of weightlessness in orbital motion. Now, by right, when a human being, for example, is in a satellite, okay, in orbit, there is always a force of gmm over r square being acted on the objects. But how we measure weight is via a contact force. So for example, right now, if I were to step on a weighing balance, the contact force is what is causing me to read my weight. Okay, but when you're moving in an orbit, there are no contact forces because of your motion. So therefore, the process of weighing cannot be accurately done, and that is why you actually feel weightless, because of the lack of contact forces. So this is explained on page 22, and you can also see how they define weight in terms of the net gravitational force acting on a body. So if, for example, you were in between two planets at a point where the net gravitational field or the net gravitational force is zero, so you would feel weightless at that point even without motion. Okay. 9.4.6 is basically using some of these concepts in examples, and that should end chapter 9.